talk about some applications of enthalpy, really important. We're going to talk about standard states and how we can use enthalpy to derive lots of valuable information in contexts that would otherwise be very difficult. So first of all, let's define standard state. So a standard state is commonly accepted as a conditions used as a reference point for the determination of properties or under other determination of properties under other different conditions, okay? So the IUPAC standard states include, if it's a gas, it's going to be like 1 bar, okay? And 1 bar is about 1 atmosphere. So sometimes standard conditions are 1 atmosphere, are just defined as 1 atmosphere. You just have to look at the table, right, at the key. So standard states, if it's a gas, 1 atmosphere, you can see 1 bar is about 1 atmosphere anyway. And let me get my marker here. And solutions, standard state of a solution is going to be 1 molar concentration. Okay, this will make more sense in just a minute. Now, when we're talking about standard states, we're oftentimes going to give a superscript of an O, okay? So in the enthalpy change symbol, that's going to be the standard heat of a reaction, okay? So the usual, but not technically standard temperature is 298, which is about 25 degrees Celsius, right? 298.15 kelvins. So a subscripted 298 is used to designate this temperature. Fine. The symbol that's used to indicate enthalpy change for a reaction is, as I put above, the standard heat of a reaction. Okay. So the enthalpy changes for many types of chemical and physical processes are available. We just look them up. They're available in reference literature. And recall that the change in enthalpy is an extensive property. It's proportional to the amount of substances involved, and but oftentimes it's normalized to the change in enthalpy per mole, right? Which sort of makes it an intensive property. All right, so the standard enthalpy of combustion, where we use a lowercase c, right, is the enthalpy change when exactly 1 mole of a substance burns, combines vigorously with oxygen. It burns under standard state conditions. So it's sometimes called the heat of combustion, right? So we would say the standard heat of combustion, we would say it like that. And an example of this is given here. The standard heat of combustion of ethanol is minus 1366.8 kilojoules per mole. That's the standard heat of combustion of ethanol, right? So here's ethanol, and we would write that reaction out like this. Here's the balanced reaction for it. And we would say the standard heat of combustion of ethanol is blank. All right, so that's for 1 mole, right? And it's done at 25 degrees Celsius and 1 atmosphere of pressure. Those are, because it's standard, right? That's what, all of that information is implied by using that little 0 right there, okay? So here's some standard molar enthalpies of combustion. Carbon, if you combust carbon, you get this. If you combust hydrogen, you get that. If you combust magnesium, you get that, and so on, right? So we can look these things up in a table. You wouldn't memorize this, of course. No chemist memorizes these things. Right? No scientist does. You always look at things up. Just need to understand it. So the standard enthalpy of formation now is given with a little f right there, right? And the standard enthalpy of formation, I think, is more accessible. I think easier. The standard enthalpy of formation is defined as the amount, the enthalpy it takes to make, watch with this, 1 mole from its components in their standard states. So carbon standard state is a solid. Oxygen standard state is a diatomic gas, right? And so to make 1 mole of this, it's going to take 1 mole of that and 1 mole of that. In the standard heat of formation, I think this is not supposed to be here. The standard heat of formation is going to equal that, okay? Kilojoules, but that's defined as 1 kilojoule per mole, or that many kilojoules per mole, right? So by definition, the standard enthalpy of formation of an element is in its most stable form is equal to 0. That's if it's an element, it's equal to 0 under standard conditions. Because if we're talking about the standard heat of formation of oxygen, well, its components are only oxygen, right? So obviously, the standard enthalpy of formation is going to be 0, right? Because you're just going from, right? So by definition, the standard enthalpy of formation of an element in its most stable form is equal to 0 under standard conditions. Okay, so we can use HESS'S law now. There are 2 ways to determine the amount of heat involved in a chemical change. We first of all measured experimentally, which is sometimes difficult to do, and sometimes we calculate it from other experimentally determined enthalpy changes. Some reactions are difficult, if not impossible, to investigate experimentally, so it's really nice to be able to use Hess's law. You've seen this before. Hess's law is as follows. If a process can be written as the sum of several stepwise processes, the enthalpy change for the total processes equals the sum of the enthalpy changes of the various steps. I'll demonstrate this in the next couple slides. Hess's law is valid because enthalpy is a state function, so it doesn't really matter how we get from the bottom of the mountain to the top of the mountain. Since it doesn't matter, we can consider it any way we like. Enthalpy changes depend only on where a chemical process starts and ends, but not on the path where it takes to start to finish. That's because it's a state function. So look at this. If we talk about the combustion of carbon, right, that's the combination of oxygen to produce the oxidized product, which is carbon dioxide in this case. The standard heat of the reaction is negative 394 kilojoules, right, for 1 mole of that. Now, if we talk instead about the standard heats of formation of carbon monoxide, oh, actually, no, we're not talking about standard heat formation. Sorry, we're talking about here, if we combust this and make carbon monoxide, and then we take carbon monoxide and combust it further to make carbon dioxide, we would find that we would get the same thing. We can just simply add those two up because these cross off, right? And when you take this, it's here. And when you add the oxygens together, you see those two being added together, you get 1, right? And then our carbon monoxide crosses off with carbon monoxide, and we get, can you see how you add those two reactions together and you get the same thing? Okay, so this is Hess's law. If you take two reactions and you can cross something off, right, you just add all this up and all the products up, and you would say that the sum reaction is going to be the sum of the enthalpies. All right, according to Hess's law, the enthalpy change of the reaction will equal the sum of the enthalpy changes of the particular steps. That's Hess's law. We see that the change in enthalpy of the overall reaction is the same whether it occurs in 1 step or 2. All right, so finally, we can also use Hess's law to determine the enthalpy change of any reaction if the corresponding enthalpies of formation of the reactants are available, which they usually are, right? I'm not going to give you something like this on a quiz or exam if you can't find those enthalpies of formation in your notes or in a textbook or in the reference material that I give you, right? So the stepwise reactions we consider are decompositions of reactants into their component elements, for which the enthalpy changes are proportional to the negative of the enthalpy, blah, 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 right? And also recombinations of elements. All right, the standard enthalpy change of the overall reaction is therefore equal to the sum of the standard. This is really what the big deal. The standard enthalpy change of the overall reaction is equal to the sum of the standard enthalpies of formation of all the products plus some of the negatives of the enthalpies of formation of all the reactants. Let's see if I can write this out. The enthalpy of a reaction is equal to the sum of the enthalpies of formation of all the products minus the enthalpies of formation of all the reactants, right? And it's going to be a sum, so you have to add up all the enthalpies of formation of all the products and all the reactants, but I should say sum, right? And that's how it works. So we'll do some examples of that in class, but really what we're doing is we're just adding and subtracting, right? We're taking all the things that are in the products, we're adding them up, and we're taking all the things that are in the reactants and adding them up. And I know that's too fast, but I'm going to cut this video off here. Let's go do some examples.